All right, good afternoon. Yeah, good. Yeah. I'm going to talk to you guys about a project we've been working on, sponsored by the NSA. Essentially, what we're doing is we have a work in progress software framework where we're focusing primarily on software in essentially post-development phase or essentially open source software. So we're looking at identifying key areas in the code, artifacts in the code, variables, which have a high chance of causing fail states in a system when subjected to data faults. We've obviously we've done research, we understand that there's a lot of frameworks out there right now which are doing static and dynamic analysis, identifying vulnerabilities in code. The issue with those, they're all very good, but they focus on looking at the software from the very beginning, the early stages of development, to guide your development process to limit the number of vulnerabilities that get introduced in the first place. We're looking at integrating complete working open source software modules into an existing system where you don't have access to a lot of the historical data for a project or who worked on it, if they followed any coding standards. Just you don't know this kind of information. You know that the open source module does what you need it to do, but you don't know how reliable it is or if it meets your security constraints, for example. So what we want to do is look to see if we can predict where you need to focus most of your attention when adding error handling and these types of things. So we place the importance of variables ranked according to impact of data faults. So what we're trying to do is get away from having to do the manual process of fault injection to figure out which one of these variables are your highest priority. Fault injection as a manual process takes quite a bit of time and effort. We have to complete the testing according to each individual module, the use case of the system. This takes time, this takes effort, this takes an understanding of how the system works so that you can design your tests accordingly. So what we're looking to do is we're building a training set, essentially, out of fault injection data, and it trains a predictive model. So given a piece of source code, we extract features, static, dynamic, and I'll talk about that in a bit. We run that through the model, and the model predicts which of the variables in the system are then going to be your highest priority, which ones have the highest chance to cause a fail state, how long your system is going to be in the fail state, how wide the failure persists. So if it gets injected in one function, does it spread to 2, 3, 4 other functions? How much your functionality then is affected by these data faults? So again, we're looking to ease the integration of these open source software modules into existing systems. And there's the research goal we've been working off of, basically to determine if features extracted from a software sample can then be used to accurately predict the trend of rankings for variables in the top 10 to 30% within a reasonable range of accuracy. The functionality will allow us to predict the top 10, 20, 30, as far down to all the rankings of all the variables in the system. Generally, you're not going to have the overhead to add error handling or focus your testing on every single variable in the system. Generally, you're going to be interested in the top maybe 10, 20%. The variables most likely to cause massive failures that persist for a long time. So again, there's a rising trend of use in open source software across a number of domains. Looking at open source software alternatives to save time and money and these types of things. But you always have to deal with, okay, we're saving the time and the money that comes from the development, but can I rely on this open source software to execute to the level of security or reliability that I would expect from code we develop in-house? So again, we're determining which variables at what parts in the code have the highest impact on the system when we inject our fault. With the goal of drastically reducing test time needed to identify these key areas and to reduce the occurrence of fail states. Fail states, whether the fail state itself is the issue, or if by causing a fail state, an attacker may be able to get a memory dump or cause your system to do something it's not intended to do, therefore giving an attacker access to part of the system it's not supposed to have, or some kind of sensitive data the system interacts with. There's a number of issues that can come up. when a fail state occurs and your system doesn't handle it gracefully. So here's just a very broad overview of how we're currently working. The user, we get source code from the user. We have to have the source code for the static analysis. One of the tools we utilize, the C language or claim static analyzer, uses symbolic execution. And so in doing so, we have to have compile information. We have to know how you're compiling the project that you're going to use, because then the symbolic execution essentially runs with the compiler and extracts information, finds bug reports, and we add the results of those bug reports to our data sets. And then the command line interface command. A major emphasis we're pushing with this body of work is, it's relative to how you want to use it. We're not going to spend time and effort testing some part of the module, for example, if the code never gets used. So if you're pulling in some existing open source software module, but you don't intend to use a third of the functionality, why waste time testing that third if the software is not going to go in that direction? So for that reason, and for the fact that we extract dynamic features from the code, we need the actual, it's all command line at the moment, so we need the actual command line code. How are you going to run this module, essentially? Then we do static and dynamic analysis to extract the features and build up a data set. The data set then gets sent to a prediction model, which has been trained by our database, which gets built up as we read in open source modules. We test them, we complete the fault injection on our end to build up the training data set. That gets used on the test data, which then outputs a ranking from 1 to however many variables you have of where your focus needs to be in the testing process. So it utilizes the software vulnerabilities and problems and defects that a lot of these other frameworks find for you, and that's fine. But we're not writing a framework to find all these common coding errors, vulnerabilities. That's already been done. We're looking at, can we take that information and use it to make an educated guess or prediction about how well your code handles data faults without having to actually do the fault injection. So the goal there is to save that time. So we have an initial experiment where we used one software project to build up a set of training data and another software project, or another piece of software as test data. So we use the MP3 game. It's just a common open source project. It regulates the gain across MP3 files. It doesn't do anything fancy, but it's got a very standard architecture. There's one hub file which calls a great deal of other files. It's a very common way to write code, so we use that as our starting point. And then in the core utilities, which we're currently in the process of testing all the core utilities to build up our data set, because there's a variety of different design elements there. We just use the move command, basically, so the command line of move. So we tested the prediction model using 2 separate data sets, one from each project, and then we tested again to try to get a feel for how the system would work given a wider variety of data. So we combined the data sets and used what's called tenfold cross-validation, which I'll talk about here in a minute, to try to get a feel for how the model would work given data it has never seen before, and then data that it's more familiar with. So here's just a brief overview of some of the extracted features that we extract at the time of this initial testing. We've since added on to these, tweaked some of these. The results indicate some features which aren't particularly useful, so we've removed them. So we've got some standard ones everyone is familiar with: Halstead's, McCabe's complexity, things like lines of code, what percentage of your code is comments, what percentage of your code are branch statements, just generic information about a file. Variable specific data, so we're interested in how many reads, how many writes, how many other variables your variable impacts. So for example, if you have a line of code z equals x plus y, well, we want to know if I inject a fault in the memory space for x, it's going to affect the value for z, and then z could go on to affect the value of other variables, if that makes sense. So we're interested in how all the code plays together. Not necessarily at a functional level, but strictly which variables touch other variables, so where's the fault spread and so on. And then dynamically, we look at frequencies, so how many times the variable is accessed. So this is why we need the command line. So if I want to run your code given the inputs you intend to use and go, okay, so this, again, z equals x plus y, gets executed 10 times in a normal run. So that means if, that value for x or y then gets accessed in that line 10 times throughout the execution of the program. So that's just something we're looking at. Size, and then we've got a couple of relative metrics. We look at probability that a memory space is corrupted. So originally what we were looking at was, for an example, like a UAV flying in a harsh environment, dust storms, things of that nature, and you actually have a hardware issue. So some of you get a data fault in that way. Some of the ones and zeros get flipped around. So we look at the probability that an error occurs in that memory space given a random application of the fault, the probability that it then gets executed. So if I inject a fault to x, for example, but then no other variable ends up calling the value for x, well then, the fault essentially doesn't have an effect. If no one relies on the value for x at that point in the program's execution, then the fault essentially sits, idle. Or if I inject a fault into x, for example, and then 2 lines down, x gets overridden with another value, then again, the fault doesn't end up having an effect. So we look at all these different types, all these different elements of how the variables get used, what values do they depend on, and things like that. And then the probability of failure, then we look at, given how often a variable will be corrupted, and then how often then it gets called. And we'll go into a bit more detail in the actual paper about how each of those is calculated. And here's just a brief overview of some of the machine learning algorithms we looked at originally. We wanted to take a very broad look. So for example, the first two are more or less baselines. 0R looks strictly at a mean choice, an average choice based on the input data. And linear regression, again, is a very common, very baseline look at the regression modeling we're going to do. And then we use the k-nearest neighbor, K-star, and local weighted learning, which are all instance-based learners or lazy learners. They rely very heavily on data points they have seen before. So they perform particularly poorly if met with data that they've never seen before, or they've never seen data quite like it. And then we have least median squared and a tree-based algorithm M5P. So again, just very baseline algorithms for a number of different, so just the mean, we have 3 instance-based, kind of rule-based, and then a tree-based algorithm. So we wanted to just take a look at very straightforward examples of the varying categories of machine learning algorithms to try to get a feel for which of these categories is best suited to pursue further research on. So here are some initial results. So basically what we did is we looked at the training and test data. So we trained the model using the MP3 game data, and then we gave it the information for move, obviously without the fault injection data. We looked strictly just at the features we had extracted, and we told it to basically predict the importance of these variables. Then, because we're not interested in the actual calculation of the importance, there's a formula which again it's a little heavy for a talk, but you can see the specifics in the proceedings. There's a calculation we do which utilizes again failure rate, temporal impact, so how long the failure persists, spatial impact, how far does it spread, these types of things. But we're not interested in the model guessing the exact value of that calculation. We want to know, does the model create the correct trend? Does it correctly guess that X, Y, and Z is ranked 1, 2, and 3? And so what this indicates is you got the true positive rate on the left and the ranking percentage on the right. So what the ranking percentage just being what percentage of the variables were attempted to be ranked. So you notice that the closer it gets to 100, the more it gets correct. The model tended to have more issues, obviously, dealing with naming just the top 10 to 20% where we're most interested in. And then the more data you give it, the better able it is to make the correct predictions. So you can look at, some of them did particularly poorly. K-star, for example, failed pretty horribly because we took 2 different software samples which had very different architecture. The MP3 game was quite a bit more complex and convoluted than Move was. And so K-star didn't really have any good data points to compare it to. So the results were extremely low. It ended up guessing 3 or 4 rankings for all the variables together because it couldn't make a hard decision. The rest performed reasonably better than that. So you see up top, the orange with the hashes, least median squared, ended up performing the best of all the models in this particular case. So you can see at 10%, it had about a 62% correct, and at 20%, it shot up to somewhere around 95%. So within the top, given the top 20% of the variables, when ranked, it was able to establish, okay, so if you have 100 variables, these 20 variables are your priority variables. These are the ones that, when subjected to data faults, cause a fail-safe the most often, and they persist the longest. So that was given data that they'd never seen before. So if we look at the combined validation set, and the way this works is basically you combine the 2 data sets together and think of like a pie graph. So we combine the 2 together, we have 100% of the data. Then a random 10% of that data gets tested on the remaining 90%. So 90% becomes the training data, and that remaining 10% is then tested on. And then another random 10% is tested on, and so on and so forth. And that happens 10 times. The idea being to try to get a look ahead and to try to see how well the model holds up when we have a stronger, more robust data set after we've been able to automate more of the process and collect more of the data. So once we build up a bigger data set with a wider variety of software projects, we can make more educated guesses as the model learns. So you can see here, some of the instance-based models started to do particularly quite a bit better than they did before, with the nearest neighbor actually being the best at 10%, actually guessed around 81, 82% correct on the rankings. So as to say that they correctly predicted the top 20% or so, 4 out of 5 variables in the correct ranking location. And so again, this is just another look at the first graph, instead looking at percent difference. So on average, how far off were the rankings from where they actually were based on the fault injection? So again, we see least median squared coming out far ahead of the others, with an average error rate in the top 10 to 20%, somewhere floating between 7% off. And again, this is using the training and test data. So you can look and see quite a few of the instance-based learners have somewhere between 25 and even 30% difference. And then we have our combined validation data set, where again, you see IVK comes much lower. So this makes sense with an instance-based learner that it would perform very well with data it had seen before. And we'll now mention this in a minute, but basically what we ended up doing is we ended up eliminating the instance-based ones for further research, just by the nature of software, we're never going to be able to build a model that has enough instances in it that it's always going to be able to go, oh, I've seen this type of code before, I've seen these types of relationships between the variables exactly as I need them to be. So we moved away from the instance-based and we're focusing more on the individual class and function-based modules, or algorithms like the least median squared and other regression types. So here's the kind of conclusions we've taken. We saw from the performance analysis that a mixture of standard software metrics, our variable-specific metrics, and then our relative metrics like probability of executing the fault once it's injected into a variable, all were found, a selection of those were found useful or impactful on the prediction process. So for example, the number of writes was found to have a high correlation with the failure rate of variables. The architecture of the system and the data flow has found to have a high impact on the prediction. The actual propagation of a fault correlated very highly with high-ranking variables and variables that reacted very negatively to getting a fault injected in them. Higher propagation, so they spread to more functions, meaning there's a higher chance for those values to be accessed and a failure state to occur. So lazy and instance-based algorithms were not a good fit for the application, which you saw, where when dealing with information they'd never seen before, the failure rate was particularly high. So future work, right now we're working on completely converting the framework code to Python. One of the major things we need is that rapid prototyping, and particularly Python's strong string processing has been useful because essentially we're doing a lot of string parsing, a lot of kind of looking through the code and making judgments, automating the process. From you for the user giving me a target piece of software and go, here's the software, here's how I use it, to getting the output back. We still have some manual aspects to the code, but we're in the process of scripting them out to make the data collection quite a bit faster. And once it's automated, we can make the code, the source framework, public, and that way it becomes much easier, obviously, to check the results of our work or to see if the framework is something that fits in with what you're doing. And then integrating additional features in the data set, like I said, we're looking at the bug reports from symbolic execution frameworks like Clang, and using the security vulnerabilities they return to see if there's a correlation between those vulnerabilities and the reliability of a piece of software. Again, this was sponsored by the NSA-CA cybersecurity program. And questions?
We have time for one question.
One question?
Going once.
Okay.
No.
So as you expand your data set and some of the programs you're looking at, do you expect to find in different classes of programs, say you use Move, do you expect to find a correlation between other file system related type programs and then maybe a different set for other like socket-based programs or different classes of software?
That's a good question. I would expect to see some correlation between the actual functionality of the code. We weren't looking there initially, but as we've been doing testing, it's become clear that depending on the functionality of the code then gets written in a particular way, and the variables are then used in a certain way. So one of the options we had considered is having a number of data sets. So if it's possible to take a look at the code and go, oh, this is a file system style code, then we train the model using our data set built on file system tests. Or if it's a socket-based networking program, then we use a data set that we built up specifically using that style of software. And so a lot of that just comes from us automating the process so that we can start building the data set very rapidly and create multiple data sets, and then we can try to tailor that in to the software we're focusing on. So that's one aspect of the future work we're looking towards.